Welcome to this presentation on Ackermann's formula. We will discuss what is meant by controller canonical form. We will explain what is meant by Ackermann's formula. We will present a solution to pole placement problem. Let's recall the pole placement problem. Here is the open loop system equation and the control law. Here is the closed loop expression. And the pole placement problem is to find k that satisfies the following equation, where we get this alpha c of z, which is the desired polynomial for controller calculation. That is what is indicated by the subscript c, possibly obtained through the desired region analysis. We want to find this k. Now let us present the controller canonical form. The pair a comma b is said to be in controller canonical form if a and b are of the following form. So a is given here. Notice that the first row has non-zero entries. You have ones here and all other terms are 0. In the sub-diagonal term we have ones, everywhere else it is 0. And the vector b has only one non-zero entry, the top row. We can show that the characteristic polynomial for this system is given by this simple expression, where the coefficients of this polynomial can be read off from here. For example, this negative of this minus a1 becomes the coefficient of n minus 1 here, and so on, and finally this an becomes the constant term in this polynomial. So this is very nice form, it gives a very nice expression, but how often can we get a and b in this form? The answer is generally we do not have our system in this form. Then what is the use? Why do we study such a system? It turns out that a general system can also be transformed into this form under some conditions which can generally be satisfied. In view of this, we do consider this system, and this form has a nice result for this polynomial. This is given as problem 14.1 in the textbook. So the next question is, if I have a and b in this form, will I get a simple expression for the feedback control law with which we obtain the closed loop state space equation? So I have this closed loop state space equation. In this, a and b appear through this a minus bk. Let us just see what happens to a minus bk. Remember, k is the row vector k1 through kn. So you write it here k1, k2 and so on all the way up to kn. So what happens when I multiply b and k? So I will have a square matrix with only top entries as k1, k2 and so on. Now I want to subtract that from here. So this becomes minus a1 minus k1, minus a2 minus k2 from the second entry and so on all the way up to minus an minus kn. That is what will happen to a minus bk. Okay. So let us go to the next slide. I have written that a minus bk. I would suggest that you calculate this and verify that you get this form as given here. So this is a minus bk. So let us evaluate phi of z, which is the determinant of zi minus a minus bk. We saw this expression before when we formed the closed loop, and because this is also in the required form, you can see that the determinant can be obtained as this polynomial where the coefficients can be read off from the top row as I mentioned in the previous slide. So this becomes the coefficient of z to the power n minus 1 with a minus sign of course, and this becomes the constant term. So the question is, can we answer this question? So can I answer this question? What is k if the desired characteristic polynomial is given by this? So this is what I want, whereas this is what I have. I want this to be equal to this. Remember, we calculate the unknowns k1 through kn by equating the coefficients. That means a1 plus k1 is alpha 1. So what is k1? K1 is nothing but alpha 1 minus a1. Similarly, an plus kn is alpha n. So kn is alpha n minus an. So I can write this in the form of a matrix. K1 through kn is given by, the first one is alpha 1 minus a1 dot 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 and alpha n minus an. So we are in a position to determine the values of entries of k by observation. The difficult problem that we had earlier, namely solving n simultaneous nonlinear equations, a difficult problem gets reduced to a simple one as given here. We would want a direct solution, however. In the previous slide we had got the expression, but for various reasons we would want a direct solution. So let us do that now. Suppose A and B are in controller canonical form, then the characteristic equation of A is given by this expression. Now let us invoke the famous Cayley-Hamilton's theorem, which basically states that a matrix satisfies its own characteristic equation. So in the place of z you substitute A and so on. So this becomes A to the power n minus 1 and A n minus 1 times A plus A n I equals 0. I is an identity matrix dimension n, which is the dimension of A also. Alright. So I have this expression. Now let me evaluate the desired characteristic polynomial alpha c of z, which is given here, which we might have got from the desired region analysis at A. Let us evaluate this alpha c z at A to arrive at alpha c of A. So that means wherever z is there we have to put A. So I get this expression. Remember to put the identity matrix here because this is a matrix equation. So you have to put the identity element here. Now let me substitute for an from this expression. An equals, if you take all of these to the right hand side, minus a1 into n minus 1. If you take all of this to the right hand side, minus a1 into a to the power n minus 1. So when I put that, this becomes alpha 1 minus a1. So let me write that, alpha 1 minus a1 into a to the power n minus 1 and so on, we get this expression. So what did we do? We solved this for an, substituted this expression here and arrived at this expression. Now this expression says we need powers of A. Here we have A, then we have A squared, A cube and so on, all the way up to a to the power n minus 1. And A and B are in a particular form. So what we will do is we will take powers of A in the next slide. So A and B are given here. Now what we will do is we will pre-multiply powers of A by En. En is the nth unit vector which has all zeros except the last entry, and of course the transpose of this, because the way we write En, it will actually be a tall vector, but I have written it as this horizontal vector into, I have written this as horizontal vector transpose. So why we want to pre-multiply, that will become clear shortly. So let us calculate En transpose times A. So I want to multiply this by all zeros but 1 here. So what this will do is, it will pick the last row, and the last row is nothing but En minus 1 transpose. So I get this. Now let us do this for A squared. En transpose times A squared is nothing but En transpose of A into A. Now what is En transpose of A? That is nothing but En minus 1 transpose of A. Now En minus 1 transpose means it will pick the second last row. So as a result, that is nothing but En minus 2 transpose. By pre-multiplying powers of A by En transpose, we get rows of A, which themselves are unit vectors. So continuing, I get this expression. So you have to remember this expression in the next slide. The way I remember this is, I subtract this power from n to get n minus 1 here, n minus 2 I get n minus 2, n minus 1 I get E1, but you might have your own method to remember this. So let us go to the next slide. Here is the expression for alpha c of A. If I pre-multiply by En transpose, I get this left hand side. Similarly on the right hand side also, I have to multiply every term by En transpose. And recall from the previous slide, either you go back and see it, or in case you remember what we said, how to remember this. This is n minus 1, it becomes E1 transpose plus dot dot dot. Here I am subtracting from n 1 here, n minus 1, and then it is Ent written directly. So can we express this in a simpler form, this particular one? Remember, E1 transpose is unit vector transpose with only the first one non-zero, that is 1. So when I multiply this, I will have alpha 1 minus A1, rest of the terms are 0 here, and so on. If you add all of them, we get this simple expression. Now can you check what this is equal to? Do you recall we derived this expression a few slides ago? Yes, this is nothing but K. We indeed derived the expression for K as given here previously. Thus the pole placing controller is given by what we have here, which is En transpose alpha c of A. And what is En transpose? En transpose is all zeros and 1. When you multiply it, it picks the last row. So this is nothing but the last row of alpha c of A. What is alpha c of A? Remember how we got alpha c? This was the desired polynomial, and then we evaluated this at A. This formula is known as the Ackermann's formula. To conclude, the controller canonical form simplifies calculations. In fact, K can be determined by observation. We also derived an explicit formula for K. This is known as the Ackermann's formula. We will make use of this formula in the general case when A and B are not in controller canonical form. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.